When the ancient fossil site on Jurassic Island was first discovered, the community was thrust into the global spotlight. For generations, this had been a quiet, untouched sanctuary, but almost overnight, the island became a magnet for scientists, tourists, and investors. For the locals, this sudden boom was both exciting and deeply unsettling. Yes, the fossil site promised new jobs, thriving businesses, and global prestige, but it also brought the immediate, suffocating reality of traffic jams, overcrowded beaches, and overwhelmed resources. This clash, opportunity versus stress, forms the heart of our study. We knew we couldn't just assume that more tourists automatically equals a worse life. We needed to measure exactly when the breaking point occurs. Therefore, our formal objective is to quantify the dynamic impact of this fossil discovery on the municipality's quality of life over a 10-year period. To do this, we developed a dimensionless output called the Quality of Life Index, denoted as QT. This is a scale from 0 to 100, representing the island's overall well-being. In layman's terms, our model asks a very simple, real-world question. What happens when the money a tourist brings is outweighed by the traffic they cause? Our core equation reflects this balance. We start with the town's baseline happiness. To that, we add the economic boost, the revenue that funds better schools and local businesses. Then, we subtract the infrastructure strain, the daily frustration of gridlock, noise, and resource drain.
Thank you, Ashok. To build our model, we first started with the visitors. We didn't use the standard exponential curve because the physical island has finite space. Instead, we use a logistic growth model. As you can see, the initial viral spike eventually plateaus at a hard carrying capacity denoted by K. Next, we evaluate how these visitors impact the town. Every visitor brings in money, so our economic submodel is linear based on the average daily spend per tourist. That is the visitor volume multiplied by C1. This represents the municipal revenue that gets reinvested into the community, funding better healthcare, schools, and public goods. But here's the catch. Infrastructure strain is not linear. The town's existing roads can only handle a max baseline capacity of ICAP. Therefore, we use a max function to ensure strain remains strictly at zero until that threshold has been breached. Once crossed, every excess person generates compounding delay hours, robbing residents of family time and introducing severe psychological stress. Finally, we bring it all together with our quality of life index. We start with a baseline score of 75 and add in normalized economic benefits before subtracting the normalized infrastructure strain. Crucially, these are modulated by societal preference weights, alpha and beta, which Ibin will now show you exactly what happens when we run the simulation.
Due to the threshold function in our infrastructure submodel, finding a purely analytical continuous solution is complex. We feel that the system is more effectively analyzed through computational simulation. Therefore, the model was solved computationally, utilizing a Python script to simulate the model from month 0 to month 120. Our simulation results illustrate the Jurassic gentrification effect, where tourism first benefits the town but later begins to harm residents as infrastructure strain builds up. Let's analyze the timeline. For the first 24 months, the quality of life increases steadily as the economic benefit grows, while visitor volume remains safely below our infrastructure capacity. The model accurately reflects that early economic windfalls genuinely improve local life. However, around month 30, the balance tips. Visitor volume surpasses the baseline capacity because the infrastructure penalty scales aggressively. The subtracted strain quickly outpaces the added economic benefit. The cost of overcrowding rises sharply. By month 40, the quality of life drops far below the initial baseline, stabilizing at a permanently degraded state as tourism plateaus at its maximum capacity. The model effectively demonstrates that unchecked tourism growth without concurrent infrastructure scaling is a net negative for residents.
Evaluating our methodology, the primary strength is the use of threshold function for infrastructure that realistically captures the non-linear nature of traffic and resource exhaustion. It avoids mathematical flaw of penalizing the quality of life for small manageable crowds. However, there are weaknesses. The model assumes the preference weights alpha and beta are static. In reality, a population's tolerance for infrastructure strain might decrease over time due to survey fatigue. Additionally, economic inflation is ignored, whereas severe cost of living increases could accidentally lower the quality of life further. In conclusion, our sensitivity analysis adds real world urgency. If infrastructure investments like better roads and waste management are not made before month 30, the decline becomes incredibly difficult to reverse. Early action can stabilize the system while delay locks the island into a cycle of stress.